Hi there, welcome to your next video. This one, we're going to take a look at solving exponential equations. So we've already taken a closer look at logarithms, but now we're going to switch it up and try to solve exponential ones. But we can use all those good properties of logs to actually help us solve. So the first example, we're going to take a look at solving exponentials in the way we've seen them in the past, where it's possible that we can rewrite the exponents. 3 to the 2x, 81. I wonder if there's a way that I can rewrite 81 to have a base of 3. Well, luckily I know 81 is really 9 times 9. And then from there, I can rewrite 81 because that is the same thing as 3 to the 4th power. I can focus on solving the exponents because if I want those numbers to be equal, should work out beautifully, and this one just happens to be at 2 for a final answer. Let's take a look at B. This one's a little trickier. I still see 2 to the x plus 1, so I'm going to go ahead and leave that like it is. Now, 1 over 8 is a little more complicated, but the good news is I do know that 1 over 8, that can be the same as 1 over 2 cubed. Now, what exponents help me bring it to the top? 2 to the negative 3, and I still have a 3x that hasn't done anything. And now I can focus on my exponents because again, I've got x plus 1, and then these are going to get multiplied. So I'm just going to have x plus 1 is equal to negative 9x, and now I can solve the way that I know how. So I can go ahead and swing this x over by subtracting on both sides. So I'm going to have 1 is equal to negative 10x, and then just divide everything by negative 10. And it works out really nicely. Well, there's no way I can make a 64 into a 16 and any way around that. But I know they both could be rewritten with a base of 4. So I'm going to have 4 squared because that's the same thing as 16. I'm going to keep the x squared on the outside because I haven't done anything with it. 64, well, that's the same thing as 4 cubed. And then I still have this pesky x on the outside. Now my bases match and I can solve the exponents. So I'm just going to have a 2x squared is equal to 3x. Well, that looks a little different than the other one. So let's go ahead and swing everything over to one side. So I'm going to subtract that 3x and try to solve. Well, I see they both have an x in common, so I'm going to factor out that x. And then I'm just going to be left with 2x minus 3. It's still going to 0. So it looks like I have 2 possibilities. I have x is equal to 0, and I have x is equal to 3/2, or 3 over 2 for a final answer. Now, these are going to look a little different because 2 to the 40th. Whoa, there's no way I can do 2 to a nice exponent gets me to 40. That is not possible. But I can rewrite using the inverse operation. So what does that mean? Well, logs are the inverse of exponentials. So what I like to do is do a little bit of rewrite. So I'm going to say log and do the swoop-de-loop. Base 2 of 40 gets me back around to x. And guess what? You've solved for x. Here's how I can show you how that number is actually just a number. So right now, we have log base 2 of 40. Yes, that's possible to do in your calculator. Hit the alpha button, and now you're going to tap on window, and you should see a familiar option, option 5. So now I can say log base 2 of 40, and I can actually get an answer. So 5.322. And that's how we can actually solve for x, which hopefully makes sense because 2 to the 5th gets me 32, and 40 is a bit higher. So that's why this answer is just slightly above 5. So we have 2 different ways of writing these. We have the exact answer, And then we have an approximation with decimals. So be very careful which form I would like you to answer in. So I'll be very clear whether you'll use the exact answer or whether you can approximate. Well, I'm going to do the inverse. So I'm going to use logs and I'm going to do a little rewrite. So log swoop base of 8.2. We've never seen decimal bases of 42.5. Deloop gets me back around to my exponent, which is now n minus 3. Well, I have a number on that side, so all I'm going to do is simply add 3 on both sides to get me a number that looks almost like that. I'm going to leave it just like this, but if you'd like, you can always check it in your calculator. Alpha, y equals option 5, so I have a base of 8.2. 42.5 plus 3. So that's around 4.782. So you can see all of these are actual answers. It's just harder for us to evaluate. So that's why we like to leave them exact, because this answer is rather ugly, but it's good to know you can actually find out the answer in your calculator. Let's go ahead and add 4 to both sides so we can get it to look like an exponential. 5x plus 1 in the exponent equaling 11. Again, there is no exponent. 5 to the first is 5. 5 squared is 25, so I can't rewrite these, but I can use logs with my swoop deloop. So I'm going to have log base 5 of 11 gets me deloop back to the exponent, which is just x plus 1. And now it looks pretty friendly because I'm just going to subtract 1 on both sides for a final answer. Log base 5 of 11 minus 1. All done. So let's take a look at one that's maybe a little more complicated, because now I think you can see I have an x on both sides. So we can still use our logs to help us. So I'm still going to do my swoop de loop. It's just going to look a wee bit different. So I'm still going to have a log, and we'll do that swoop. So I've got base 5 of 3 to the x. So base 5 of 3 to the x. Deloop gets me back around to x plus 1. All right, I know what you're thinking. That's not helpful. So here's where we're going to use our properties, because I see an exponent, a literal x in the exponent. So that means I can use my properties and swing that to the front and multiply those by one another. All right, it looks like I have an x on both sides. So let's go ahead and bring all of those x's over to one side. So I'm going to subtract that x on both sides. So I moved that x and brought it on over. Now I see both of these have an x. So why don't we just take the x out of both? So I'm going to have a log base 5 of 3 minus 1. I still have it equal to -1. Looks like I'm almost there. I'm almost done solving for x because I've got x times, again, I don't know what this number is, but I know it's a number. So I can just divide both sides by that log base 5 of 3 minus 1. And that is a final answer for x. So for the first step, let's go ahead and do our log base 16 swoop 3 to the 3 minus d, d loop. So I've got d minus 4. We're going to do the same thing every time I see a power. We're going to swing it to the very front of that log. So I'm going to have 3 minus d times log base 16 of 3. That's just a number, so I've left that in purple. I still have the d minus 4, nothing more to do there. Now this next step is where it's going to get a little weird, because we are going to distribute that number, log base 16 of 3 to here, and I'm going to distribute to here. So there's where I got both of those, and you'll see where that negative kind of got carried over. I'm just going to copy this down. I still have a d and a minus 4. So now I've got numbers and variables on both sides. So we're going to go ahead and separate them. So we are going to put all of our numbers on one side. So I'm going to add 4 to the other side, and I'm going to get anything with a variable on the other side. So I'm going to add that d log 16 of 3. All right, I see both of those have a D. So all I'm going to do is say you have a D, you have a D. I'm going to factor out a D. So I just have this number left. And it's almost like the last example. So I can see that both of these are getting multiplied. So if I need to solve for D, I'm just going to divide both sides by that number. So now these cancel out, and I have the D all by itself for a final answer. So I've got 3 log base 16 of 3 plus 4, all divided by 1 plus log base 16 of 3. That's a final answer where you're going to leave it just like that. Again, that is an exact answer. If you would like to see what it looks like in your calculator, so I'm going to choose alpha and y equals to give myself a nice fraction. Then I'm going to do 3, and I need a log with a base of 16. So the alpha window, option 5, base 16 of 3 plus 4, all divided by 1 plus alpha window, option 5, base 16 again of 3. So final answer is somewhere around 3.716. So I'm going to still do the same thing and rewrite and use log. So I've got log base 5 swoop to the orange. So that's my big loop. So base 5 swoop to here gets me back to my exponent. So the green equal to 4x minus 2. Anything with a power we can bring to the front and we can multiply. So I'm going to have 3 minus 2x times log base 5 of 2 still equal to 4x minus 2. Then I'm going to go ahead and distribute that number, that log base 5 of 2. So I can distribute. So here's where I can multiply here in the green. And then here's where I can distribute. Again, it's just a number. Similarly, on the last one, I've got numbers and variables on both sides. So let's go ahead and separate those out. So I'm going to add 2 to both sides. And I'm going to add that 2x log base 5 of 2 onto the other side. We're going to do something similar. I see both of these have an x. So I'm going to leave this side alone, nothing more to do. But I'm going to factor an x out of both. So I'm going to be left with 4 plus 2 log base 5 of 2. Similarly, on those last ones, these are going to get multiplied. So I'm going to divide both sides by that green number to get this for my final answer in red. So 3 log base 5 of 2 plus 2, all divided by 4 plus 2 log base 5 of 2. All right, this is our last one. Nahum and Nathan are working diligently to solve the equation below. They are going to try graphing instead of solving algebraically. So on this one, take a closer look and think about why graphing would be an easier method compared to trying to do this algebraically like we have seen in the past. I do see a regular log. It looks like the base is missing. So I'm going to go ahead and add 10 because that's our common log. So I've got a base of 10. Well, that one has a base of 10. This one has a base of 2. These look like completely different equations because I have exponentials on one side, and then I've got a log on the other side. So this one, I think you can see why graphing is going to be a little bit easier. Not only are they different types of equations, they also don't have the same base. So trying to convert between those isn't going to be easy. And I feel like I'm just going to be doing a lot of rotating around. So I can see this vertical asymptote here on that blue graph. So that is going to be my log graph. And then here's that horizontal asymptote for the red. So that most likely is going to be my exponential. So what you can do if you want to use your calculator instead of Desmos, you're basically doing y1 and y2. And hopefully your job is to see where both of these functions would be equal to one another. So if I plug in an x, where would these functions be equal? Hopefully you can see this nice intersection point right here. That is currently on both graphs. which means that is exactly where they would be equal to. So here, x would happen to be 30 for a final answer. So here you can see I went ahead and plugged in my 30 to both sides just to confirm, and you will actually see that both sides will equal 2.